Today we will discuss about what is Dining Philosophers Problem and the solution for it. First, we will try to understand what is Dining Philosophers Problem. It says that there are philosophers. Here I have considered 5. So you can see here 0, 1, 2, 3 and 4. So there are 5 philosophers. It can be 2 also. These philosophers share a circular table. So this is a circular table which I have shown here. Surrounded by 5 chairs, each belonging to one philosopher. What these philosophers do? They either eat or think. So there is a bowl of rice here. Okay. There is a bowl of rice kept at the center of the table with 5 single chopsticks. So these are the chopsticks which I have shown 0, 1, 2, 3 and 4. To eat rice, each person should have 2 chopsticks. Hence, to solve the problem, they have to share the chopsticks among them. When they think, they don't have to share, but when they want to eat, they have to share the chopsticks. So suppose philosopher 1 wants to eat, then she will need chopstick number 1 and chopstick number 2. If philosopher 4 wants to eat, then she will need chopstick number 4 and chopstick number 0. We have studied the critical section problem in previous lectures. Whenever the process works, that time either it works in its initial or remainder section. That time it is independent. Means the process is not sharing anything with other processes, but when process is working in the critical section, it accesses shared resources. Here in this problem, which is that critical resource? The bowl of rice is not a critical section because more than one philosopher can access the bowl at a time. For example, philosopher 1 and 3 can eat simultaneously. So now, which is the critical section? Is chopstick a critical section? Yes. Why? Because one chopstick is shared between 2 philosophers. It is a shared resource between 2 philosophers. When one philosopher is eating another, at the same time, another cannot eat. Here we have 5 chopsticks. Means in this problem, we have 5 different critical sections. So using semaphores, we can solve this problem. Now we will see how to solve this problem. Here we are going to use array of semaphores. Now we know that there are 5 critical sections due to 5 chopsticks. Initially all the elements of array are set to 1, which indicates that all 5 chopsticks are available. As soon as chopstick is in use, the corresponding array element is set to 0. The array index indicates chopstick numbers. So here we have 5 chopsticks, so there are 5 elements. For 5 chopsticks, there are 5 array elements. Here the solution is given for philosopher number I. So this is the solution solution for this particular problem. Here I have used a while loop. So this loop will be executed till the condition is true. As mentioned in the problem, the philosopher is either thinking or eating. When the philosopher is thinking, that time she is not interacting with any other philosopher. Means she is in initial section. Before start eating, what she has to do is, okay, for example, I am taking I is equal to 1 here. So philosopher 1. Okay. So for philosopher 1, okay, she needs chopstick number 1 and 2. Okay. So here she has to perform 2 weight operations on chopstick number 1 and chopstick number 2. Okay. How we'll get 2 here? I is equal to 1. So 1 plus 1 mod of 5 is 2. Okay, so there will be two wait operations performed by philosopher 1. Okay, so why we have used mod 5 here, that I will explain you later. So for I equal to 1, we will perform wait operations on chopstick 1 and 2. So here in the array for index 1 and 2, we are going to set the array element to 0 from 1. So 0 indicates that chopstick number 1 and 2 are not available for any other philosopher because it is being used by philosopher 1. Okay. Now at the same time, if philosopher 2 wants to eat, then for her also we have to run the same code. Okay, so for I equal to 2 now, what will happen? Because philosopher 2 wants the chopstick number 2 and chopstick number 3. Okay, so is it possible to assign chopstick number 2 to philosopher 2? No. Why? Because index 2 here, okay, what is the value of index 2 here? 0, and 0 indicates that chopstick 2 is not available for any other philosopher because philosopher 1 is already using that chopstick. Okay, so philosopher 2 will keep waiting for chopstick number 2. So by using this solution, we can allocate one chopstick to only one philosopher at a time. Another important thing, why we have used mod 5 here. Okay, you can see here we have philosopher 0, 1, 2, 3 and 4. After 4, okay, we don't have the value 5, right? We have value 0. So philosopher 4 wants chopstick number 4 and chopstick number 0, right? So for I equal to 4, what will happen here? What will happen here? Okay, for I equal to 4, it will be 4 plus 1 mod of 5. So 5 mod of 5 is 0. So chopstick number 0. So this is how we'll get chopstick number 0. Okay, that's why we are using mod 5. Now, what is the disadvantage of this approach? The deadlock can occur. Initially, all chopsticks are available. So suppose for philosopher 0, okay, philosopher 0, where is philosopher 0? Yeah, philosopher 0 needs chopstick number 0 and chopstick number 1. So for I equal to 0, okay, chopstick 0 is assigned, okay, and this is chopstick 1, right? So for I equal to 0, for philosopher 0, chopstick 0 is assigned, okay. Now before assigning chopstick number 1, if in between these two, if the context switching happens. Now what is context switching? That we have already learned. The control will go to operating system. Okay. At the meantime, in between, philosopher 1 comes into the picture or comes inside, and the chopstick 1 is assigned to philosopher 1. And again, in between these two, the context switching happens. Okay. Similarly, for philosopher 2, if the chopstick 2 is assigned, okay, what I told you, philosopher 0 we have assigned chopstick 0, philosopher 1 we have assigned chopstick 1, and philosopher 2 to 2, then philosopher 3 may be 3, and so on. Okay, so what will happen in this case? The deadlock will occur. Why? Because philosopher 0 wants 0 and 1, philosopher 1 wants 1 and 2, philosopher 2 wants 2 and 3, and so on. Okay, but the second chopstick is not available. It is available with some other philosopher, and that philosopher will not release that chopstick till he or she completes its task. Okay, so this is how the deadlock situation occurs, and this is the disadvantage of this approach. So in this code, after eat we have used this signal, okay, to release the resources. To release means, suppose a philosopher 1 is using chopstick number 1 and 2, and after eating, okay, philosopher 1 should release the resources, that is chopsticks. So this is the code we have used to release the chopsticks. Okay, now what is the solution for this deadlock? So there are three ways. The first solution is to use one more semaphore inside thinking. So after this we can use a semaphore, one more semaphore PS, and here after this you can use this PS. Okay, so this is weight of weight, and this is weight of S, and this is signal of S. Okay, so initially S should set to 1. Okay, by default the value of S is 1. Okay, so 1 indicates that it is available and 0 indicates it's locked. Okay, so the philosopher who wants to pick up the chopstick will make the value of S to 0. Okay, then only it can go inside. Okay, so this is again here we are treating this section as a critical section. Okay, so it is available to one of the philosopher only at a particular time. So we are treating this as a critical section, hence no one else can access the same chopstick, okay, at the same time. Another philosopher can context switch but cannot access the chopstick. This is how we ensure that one philosopher will get both the chopsticks. Problem with this solution is the overhead has increased due to use of one more semaphore. The second solution to reduce the cost and time or overheads is, instead of 5 philosophers, we will allow only 4 philosophers to sit on the table. Doing this, we are allowing 5 chopsticks and 4 philosophers. So initially, at least one of the philosopher will get 2 chopsticks. Once that philosopher finish eating, she will release the chopstick and will be available for another philosopher. In short, if there are n processes, then we will use n plus 1 resources. The third solution can be use 6 chopsticks and 5 philosophers. The additional chopstick can be used by one of the philosopher, and after eating she will release the chopstick and will be available for another philosopher. The fourth solution is to allow a philosopher to pick up her chopstick only if both the chopsticks are available. To do this, she must pick up the chopstick in a critical section. So, in this second, third and fourth solution, cost is less, but we are changing the problem statement itself. So we have discussed 4 solutions. Depending upon the requirement, one can decide which solution he or she should use.